Okay, thank you. So so this is day 4, but it's a lie because we already talked about this yesterday. So we have this notion of positive flag quadruples, where we have 4 flags. And we say that this flag quadruple is positive if, so if I add a diagonal like this, I've decomposed the fourth thing, the quadruple into 2 triples. One is F1, F2, F3, and F1, F3, F4. And so it's positive is the triple ratios of these flag triples are positive. And then if addition, with the diagonal here, I have a double ratio corresponding to F1, F3, M4, and 5. And I also want that to be positive. And what I said is that it's invariant under the symmetries of the square, namely under cyclic permutation. And so cyclic permutation is hard because when you rotate the square, this diagonal turns into that diagonal. So we needed our analysis of diagonal exchanges using stingrays and so on. And then on the other hand, there is also symmetry by reflection. That one was pretty trivial. Okay. And so as I said, the reflection, on the other hand, is pretty trivial. Okay, and then where I stopped yesterday was in the following. This result we had seen before, and he says that if you give yourself positive numbers, you can realize them as triple ratios and double ratios of a flag quadruple in that sense. And to connect that to what I was doing at the beginning, there is the statement that a positive flag quadruple satisfies the maximum span property. Namely, that's what namely these are special cases of these maximal span flag tuples. And the reason is because to show, so we had shown when studying diagonal exchanges with stingrays and so on, we were considering these wedge products, W, so previously ABCD, now they are called A1, A2, A3, A4, and the associated wedge product of these. And to show that the corresponding subspaces form a direct sum, it's enough to show that this is non-zero. Okay, so, and we had a result which said that all of these we could express in terms of the wedge products that are in the top stingray. Okay, now there is a little lemma, it's combinatorial, which says that if the double ratios and triple ratios in the top stingray are all positive, then you can choose these elements in the exterior power so that the wedge products in this top stingray are always positive. And it's because when you take a triple ratio, you're taking well, it's a triple ratio, so you have 6 wedge products like this. And if the product, if the triple ratio is positive, that tells you something about the signs of these 6 wedge products. It tells you that they go together. And so you play a little bit with the combinatorics, seeing what you can change and what you cannot change. It's a very easy lemma. And so you can make all of those here positive. Well, and also, so we had that result, which was much deeper, which says that this wedge product, you can always express it as a rational function with non-negative coefficients in these positive numbers. And so in particular, it's positive, and it's positive, it's not zero. And so that guarantees that this is never zero. And so because it's never zero, that also guarantees that the sum is the whole space, because if it was less than that, then you would have linear relations and the wedge product would be zero, and which is exactly what we wanted. Okay, so that's a proof based on stingray. And then later today, we're going to see another proof, which is based on something deeper. And this deeper thing, which is actually what's underlying the whole theory. So there are two ways to see what I'm talking about this week. One is the very concrete way which I've been developing so far. But that doesn't explain how it was found in the first place. It's not that God said, and there will be triple ratios. I think, so I don't know exactly how Fock-Goncharov thought about these things, but certainly there was this idea of totally positive matrices, which was in the background, and they made the connection with that, and they understood everything, and that's what's behind that. And my goal is to explain a little bit the connection. So that's what I'm going to try to do today and tomorrow. Okay, so, but right now, so I'm not supposed to do this. I don't like it too much. Okay. So the upshot of what I just said is that the positive flag quadruples are maximal span flag quadruples, so they are contained in the maximal span flag quadruple. And in fact, they are a whole component of that space. And the reason for that is because, well, this is defined by a positivity of certain invariants. Okay, now if you go to infinity in that space, that means that your positive invariants are not positive numbers anymore in the limit. So either they go to infinity, well, that means that you are going to infinity in the, so you are losing the, well, either you go to infinity or to zero, that guarantees that you are losing the maximal span property. So that's how you show that it's a whole component. That's, it's a relatively naive way of understanding this, but it works. Okay, so in the space of maximum span flag quadruples, you have this very nice component. And as we saw in the case where n is equal to 3, on the other hand, the other components are messy. They are really hard to understand. Or at least they are defined by weird conditions and so on. Okay, so that's it about flag quadruples. And so, so let me summarize what we've seen so far. First, we started by considering flag pairs, transverse, but that's equivalent to maximum span. That was very easy. There was only one up to the action of GLN. Flag triples, there was a whole modular space determined by triple ratios. And then flag quadruples, well, there was a modular space determined by these triple ratios and double ratios. Okay, so now we keep going, and we are going to talk about flag quintuples. No, just kidding. And then sextuples, and then heptuples? I'm not sure. No, we go straight to p-tuples. So we go to p. And to p, we have to understand, so we have a list of p flags, and we're going to use a triangulation of this list. So here is a purely combinatorial object, and so you have an order list of objects, which of course will be flags right away, but that could be cups on the table or whatever. So you have a list of, in this case, 7 objects. And so, and it's cyclic, you consider that list up to cyclic ordering. And so one good way to understand them up to cyclic ordering is to see them in a cycle, namely as the boundary of a polygon, write them at the vertices of a polygon. Right? And then a triangulation of the list, that's just a triangulation of the polygon where all the vertices are at the vertices of the polygon, namely no interior vertices in that triangulation. Okay, so it's going to be something like this. That's a typical example. Right? And it's a well-known combinatorial object. Actually, so sort of knew it. You can rephrase that in terms of binomial, binary trees, or in mathematics, you know, there are these horrible parts of algebraic topology nowadays, which is based on how many brackets how can you put brackets when you do some operation, and interesting. I mean, what's amazing is that you can do some very interesting mathematics just looking at that. That's really the amazing part. So in topology, we begin to be familiar with this way of saying. I looked up the Wikipedia page. There are these things occur in so many contexts, and in particular, the number of triangulations like this. This is the Catalan number. So the fact that it's the Catalan numbers tells you that you can find these everywhere. That's okay. So that's a combinatorial object that you can rephrase differently, but seeing in a triangle is a little closer to what we want to do. And so I'm going to talk about positive flag p-tuples. So we fix a triangulation like that, like what there was in the previous slide. And so I have to see. And we take one such that for every triangle, the corresponding flag triple satisfies the maximum span property. So if you do that, you can define triple ratios for each of these these flag triple, and also double ratios for each edge of for each edge of the triangulation. And if I didn't mess up, this is the number of triple ratios, and this is the number of double ratios, like this. And then we're going to say that the p-tuple here is positive if all of these numbers are positive. So it's exactly like what we did with quadruples. And so it's going to be positive, but this definition depends on the triangulation. So the result is the p-tuple is positive with respect to the triangulation. However, there is a proposition, which is that if it's positive with respect to some triangulation, it's positive with respect to all triangulations. So so you don't have to worry about fixing a triangulation. It's sort of universal. And the reason for that, it's because there is a combinatorial result, which is well known, which is that given two triangulations of the polygon, you can always go from one to the other through a sequence of diagonal exchanges. Well, if you do binary trees, these are known as flips. If you do brackets, I don't know how they are called for brackets, but I mean it's a well-known result in many branches of mathematics, and it's purely elementary. It's not that easy to prove, actually. Okay, and the result is that once we fix a triangulation, so we have these triple ratios and with double ratios, and they satisfy, they provide a parametrization of the set of positive flag triples by R plus times to the power of the number of invariants. That's this number here corresponds to the triple ratio. This one corresponds to the double ratios. Okay, so it's exactly what we've done so far. And then theorem, every positive flag p tuple is satisfy the maximum span property. Okay, so we could, if you remember, we had snakes, we had stingrays. Well, so perhaps here we have more, P is getting bigger. So we could, to understand what's happening, we could get two-dimensional stingrays. I don't know exactly what they are, or P minus one dimensional stingrays. But that's too hard. So we will see a proof using totally positive matrices. And that's the next slide. Okay, so it's a weird notion. So totally positive matrices, it's a weird notion which goes back to, so I'm going to quote, so I want to look at one result from 1951, late 40s. Right? Okay, so you know what, if you have a matrix, an n by n matrix, we say it's positive, not totally, just simply positive if all of these entries are positive, strictly positive, not zero. And you know, there is a famous result in that area because it comes up, it's well known for people doing dynamical systems, for instance. We see that if you have a positive matrix, it admits an eigenvalue which is nicer than all the other ones. First of all, it's real, and then it's larger than all the modulus of any other eigenvalue, including the complex ones. In addition, but I don't think we're going to need that, the eigenspace has dimension 1. So it's okay, for people, like if you know the word pseudo-Anosov, that's where the stretching factor comes from, for instance, to talk about this kind of mathematics. But in dynamical systems, that comes up as entropy and so on. Okay, so that's positive. It's a very natural notion because yeah, in a matrix, when you notice that all the entries are positive, this is clearly telling you something. Totally positive, on the other hand, it's weird because we're going to say that a matrix is totally positive if all of its minors are positive. So what's a minor of a matrix? You have to remember, you take k rows, you take k columns somewhere, and then you take the intersection. So you get a k by k matrix. And so that's the minor, and you take the determinant. And so you want those determinants to be positive. So in particular, if you take the one by one determinants, namely that's called an entry of the matrix, then they have to be positive. So if you're totally positive, you're positive. But if you're positive, you're not necessarily totally positive. Okay, now this definition is weird. There is a better way of understanding this if you look at exterior powers, because the kth exterior power has a basis. So if E1, En is the standard basis on Rn, if you take the wedge product of EI1, EI2, EIK, where the ij's increase like this, that forms a basis for the exterior power. Okay, that's a property of the exterior power. And the matrix is totally positive if, when you express its action on the exterior power, its matrix is positive in this basis. In other words, if you look at the image of that element, so it's a linear combination of elements like that with positive coefficients. So that's the better way of understanding what this means. And in particular, if you see it like this, it's pretty clear. So there is a lemma, which is that if you take two positive matrices, their product is positive. Well, okay, it's obvious. If you know how to multiply the matrices, it's pretty clear. Eh? Okay, and so if you apply this to the maps induced on the extra power, it's pretty clear that the set of totally positive matrices is stable under multiplication. I mean, the product of two totally positive matrices is totally positive. By the way, a totally positive matrix is invertible because if you take the n by n minor, namely the determinant, it has to be strictly positive. Eh? So you're in GLN, not, whereas this notion, you're only in MN. Eh? Okay. And then a nice application of this. So by successive application of Perron-Frobenius to the maps induced on the exterior power, you find that if A is totally positive, then all of its eigenvalues are real, distinct, and positive. So you can order them like this. And the reason for that, so first you apply it on the action of A on Rn. So that's what's going to give you lambda 1. Lambda 1 is the lambda you have here. And then you apply the formula to the action on lambda 2 of Rn, because the eigenvalues of the action on the second exterior power, that's the products of two eigenvalues. Okay, so now you try to figure out which one is larger. That's going to be lambda 1, lambda 2. So lambda 1, lambda 2 has to be real and larger than anybody else, and then you keep doing it. So it's relatively simple. And my understanding is that it's for that reason that the notion was introduced. Namely, so it's, I mean, this is, people quote people at Stanford who were using linear algebra, but with an eye towards application to economics. And so they want a criterion which was stable under multiplication and which guaranteed that all the eigenvalues were real. So that's my understanding about where this came from. Okay, now the problem, we've been talking about flags. And with flags, you have a lot of triangular matrices instead, upper and lower triangular, like many of my maps were like that. So triangular maps are usually not very totally positive because they have zeros, right? They are not, they are usually not even positive, right? Okay, so there is a notion of total positivity adapted to triangular matrices. So I looked at the field, they call that totally positive triangular matrices, but then a triangular matrix is not totally, I mean, a totally positive triangular matrix is not totally positive, which I find disturbing. So I decided to use instead triangular positive, namely it's a positivity adapted to triangular matrices. Okay, and there is an upper and lower version. Okay, so we're going to say that it's upper triangular positive with a hyphen. If it's upper triangular, okay, that we know what that is. And if it's trying really hard to be totally positive, namely if every minor that is not obliged to be zero by the triangular property is positive. So then I wrote what that means here, but don't try to understand that. Just it's as totally positive as possible, knowing that it's a triangular. Okay, and then there is a notion of lower triangular positive. Same, I said, an easy way to say it is that if the transpose is upper triangular positive. Okay, and we have encountered these before, because if you remember, our classification of maximum flag triple, we had, you remember, associated to the bottom snake, we had a basis for the dual of R and to the power n, and we had another basis associated to the top snake, and we had an explicit formula for the base of change matrix. And if you remember the shape of the base, it's pretty clear that it's non-negative. I mean, it had a lot of zeros, but it was only associated to one move. So it's non-negative, and the claim is that when you do all the moves, when you move the snake all the way from the bottom to the top, then you're going to have something which is as totally positive as possible. That's okay. So that's, you observe that, and so these base of change matrix is is lower triangular positive only if the triple ratios are positive, but that's what we're interested in. Okay, so it's lower triangular positive, but you may remember that we used that to create a map between the duals, and then we took the transpose, and so the transpose is going to be upper lower triangular positive, but upper triangular positive, but it's the same. Okay, and then another example is that if you have A, which is upper triangular positive, and B, that is lower triangular positive, then the product, so if you take two triangular matrices where where all the non-zero entries are positive, then when you take the product, all the entries are positive. That's again, you just need to know how to multiply matrices to see that. Well, so here again, the product will be totally positive. That's going to play a role later on in what we do, because then in particular, it has this nice property of eigenvalues. Okay, and then I'm going to mention this result here. We are not going to use it, but so when you try to understand the algebraic structure of GLN, well, you have the maximal torus, that's the diagonal matrices. And then you have the Borel subgroup, which is so one is the upper triangular matrices, and there is the other opposite Borel subgroup, which is the lower triangular matrices. And, if you want to mix them, it's useful to consider the upper triangular with only one on the diagonal. They're called the unipotent matrices. So you have UN plus of R, UN minus of R, and the diagonals. And then if you're interested in this positivity property, you can take the upper unipotent matrices that are triangular positive, the lower unipotent matrices that are triangular positive, and the diagonal matrices where all the diagonal entries are positive. And then you have the theorem of Anne Whitney, so namely not the topological Whitney, from 1951. I just looked her up a little bit. It's actually interesting and a little sad. So she wrote that very influential paper in 1951, and then she got married in 1952 and stopped doing any mathematics at all, and seems to have resented it 40 years later. Yeah, so different times. We show that you have, so if you don't care about positivity, there is a well-known decomposition of the fact that GLN is the product, you can express every matrix as the product of the lower unipotent matrix, a diagonal matrix, and then upper unipotent matrix, and then you can put positive everywhere. So you have this unique decomposition as a product, which mirrors the which mirrors what exists when you don't care about the word, okay, already I'm here. When you don't care about the word positive, and which shows you that there is something deep going on. And indeed, so this guy, Lustig, who's a very famous, I don't know, representation theorist or whatever, I mean, he does lots of things, noticed that and jumped on that to realize that these notions here, you can extend to more general Lie groups. And the correct statement is that to split algebraic Lie groups. So split means that you have a pair of opposite Borel subgroups. But that's what triggered his theory of positivity in Lie groups. What?
Oh, minus sign. Positive.
Yeah, yeah. So minus means lower. You know what? Yes, but U is unipotent. It's not upper. I actually thought of that. It turns out that those guys, they actually use a very similar notation with plus and minus, except that they don't even tell you what that is. So they use the letters U and D and H without telling you what that is. See, I have a few, less hair than I used to, and they contributed to it. Okay, so application to positive to flag T tuples. So I'm going to use this to prove that every positive P tuple of flags satisfies the maximum span property. So what does that mean? That means that we want to show that you give yourself dimensions adding up to n, you create these exterior powers, and that should be non-zero for any for some choice. It's enough to do it for some choice of non-zero elements in the exterior power. And so we do this by induction. And for that, we need to triangulate the list F1, F2, F3, Fp, and we're going to triangulate it as a fan. So it looks like this picture here. You know, a fan would have been really useful in Dijon this week. And, okay, so. And so here is the fan, and I'm going to do things by induction. And what I noticed, so I'm going to put the emphasis of F1, Fp, because I'm trying to do an induction. And now you remember, so let's look at the triangle F1, Fp, Fp minus 1. You know, to define triple ratios and so on, I had my discrete triangle there, and I had the gray triangles. So I only drew the gray triangles that are near the edge. I had many more gray triangles. I didn't draw them. So I have all these gray triangles which corresponded to the bottom snake in this triangle. And we had the bottom snake, and so we had a projective basis associated to that. And I'm going to normalize my, you know, this property is invariant under the action of GLN. So I'm free to move my flag by an element of GLN. So I'm going to do that to normalize it so that this projective basis is the standard basis of Rn. Okay, so I told you, yes, I remember, no glasses. Yeah, so I told you I've been complaining about the way this paper of Fock-Goncharov is written because there are many things that are difficult to read there. In particular, they switch back and forth between the space and the dual without saying it. And because I've rushed to write this note yesterday, well, I did the same thing. And I just noticed. No, sorry. It's because Su Young put the wrong, the wrong version of the notes on the computer. So I will correct that. Because this is a basis in the dual, and this is a basis in Rn. So what I mean is that the projective basis is the dual basis of this one. I mean, okay. Or more precisely, I'm meaning that the dual basis of the, but then it's hard to read. The dual basis of the projective basis associated to the bottom snake is the standard base. Yeah, so Fock-Goncharov have an excuse to also skip this kind of subtleties. And so what we will prove is that once it's normalized like this, and so I want to show that the wedge product is non-zero. And so I'm going to prove by induction, I'm going to prove something that is stronger. And stronger is that instead of taking dimensions whose sum is exactly n, I'm only going to require that it's at most n. So certainly if it's true for anything that is at most n, it's going to be true for n. And so what I want the first, because of my normalization, I want the first element to be the product of the first A1 vectors in the standard basis of Rn. FP, AP, the pth one is the last AP vectors in that basis. And then when you take the product of all of them, so again, there is a mistake here, because if the very first vectors here are these, and the last vector here are those, when you take the product, necessarily in these terms, you're going to have that the first ones are these, and the last one are these here. So what I mean is that there will be this guy in here, and that guy here at the end. So that will be correct in the new version. So I think you guys are going to post these notes, these corrected notes eventually on the web, right? Yeah, so I will correct that by that time. But that's the essentially what this says is that the wedge product is a sum over all the reasonable elements of the exterior power with positive coefficients. That's the important property. Okay, and so the proof is a little complicated, and in particular, if you try to read it, it's going to be a little bit of a pain, but I'm just going to emphasize the key words. So we want to do it by induction. So we're going to consider so we start and we assume that the property is to p minus 1, and we consider a family of p flags like this. Okay, but now because we do the induction, we consider the first p minus 1 flags, and that one is not normalized anymore because well, I should alternate with the picture I had before. Nope, that's this sense. Now I'm considering this edge here, and I'm considering so the projective base I associate to this snake here is the standard basis, but the ones associated to this snake there is no reason for it to be the standard basis. Okay, so, but I'm going to use the change of basis going from here to there to normalize. So I take the change. I'm going to say it with words. It's much easier than seeing the formulas I have written in the notes. The change of basis send the bases associated to this bottom snake in this triangle to the snake associated to the top snake of this triangle, namely the one associated to these gray triangles here. Now, I'm caring about the one associated to the triangles on the other side. Now, they are not the same. They are just adapted to the same flag pair. They differ by rescaling each individual vector. And actually, the rescaling of these vectors is exactly determined by the double ratios. That's what the double ratios measure. So, in particular, if the double ratios are positive, and also the map sending this basis to the basis according to, associated to this triangle here, that map is, I said, is triangular positive. And then to go from this basis to the one on the other side, you multiply by, you rescale by positive numbers. So it's still going to be triangular positive. So there is a map going from here, sending this basis here to that one, which is triangular positive. Okay, and then blah, 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 blah. So you put things together. So it was really important that that thing is triangular positive. And then you put everything together and you conclude that after a choice for the elements that involves this change of basis matrix, then you realize the hypothesis. So it's not hard. It's a little hard to explain, and I'm going to lose you. So I think I'm going to skip it and. You can look at the notes if you, once I have corrected them, and to get a formal proof. But really, what I want to emphasize is that what we used here is the fact that the change of basis metric was triangular positive, namely the one we determined using snakes. That was that's the key ingredient. And then this idea of positivity. Okay. And then now we have the same result we had for positive p-tuples. Namely, positive t-tuples are contained in maximum span p-tuples. And so once you know they are contained, they form a whole component, because the only way you can stop being positive if some of these ratios becomes zero or infinity, namely if you move away from the maximum span flag quadruples, and then you have a parametrization by R plus to the number of invariants. And I think, so let me see, but I think, yes. And I think I would like to stop here today. And tomorrow, we're going to... So today, I want you to get the key idea that underlying the whole theory, there is this notion of totally positive matrices. And then tomorrow, we've done configuration of flags or polygons, but polygons are boring. So we're going to switch to surfaces, right? And then we did all the work to do that on surfaces of general topology, non-compact surfaces of general topology. Doing it for compact surfaces is much harder. Okay, so that will be tomorrow. Thank you.